Thank you very much for the introduction. So first of all, I'd like to thank the organizers for giving me opportunity to present our experimental activities of to study three-nucleon forces. So introduction. Now three-nucleon force, that's a nuclear forces acting in systems more than 2 nucleons, are now taken as key elements to understand various properties of nucleus. The existence of three-nucleon force of itself was predicted just after Yukawa's meson theory, but the first indication of three-nucleon force was predicted in the binding energy of triton. And since the 1990s, the evidence and the candidates of three-nucleon force effects have been reported and or predicted, like as in a few nucleon systems, in the binding energy of light mass nuclei and nuclear matter properties. The background of the significance of three-nucleon force comes from the fact that nuclear potentials have achieved two very realistic ones, which reproduce 3,000 or 4,000 nucleon scattering data, as well as neutron properties. The first theoretical insight of three-nucleon force was predicted by Fujita and Miyazawa in 1957. What they proposed is two-pion exchange type three-nucleon force, where the delta iceberg citations are intermediate state. So this picture shows that three-nucleon force naturally arises due to the inner structure of nucleons. And then later, the more refined three-nucleon forces are often used in the calculations, such as Tucson-Melbourne three-nucleon force and Urbana-9 three-nucleon force, and Brazil or Texas three-nucleon forces. Basically, these three-nucleon force models are a two-pion exchange type of three-nucleon forces. And nowadays, the three-nucleon forces have been discussed based on chiral effective field theory. And then three-nucleon forces appear at next leading order, which also includes the Fujita-Miyazawa type three-nucleon forces. However, it is very hard to approach three-nucleon force experimentally. So where can we see three-nucleon force effects? A good example came from ab initio calculations such as green function Monte Carlo and no-code shell model calculations. Here it's shown that the calculated results are based on green function Monte Carlo based on argon V18 potentials together with Urbana-9 and Illinois type of three-nucleon forces. There are so many results, so I pick up two examples. That is binding energy of helium-4 and the binding energy of helium-8. And the experimental binding energy is shown here. And the calculated results based on two nucleon forces, that is AV18, are shown here. As you see, there is a large discrepancy exists between the data and the calculations based on two nucleon forces. And these caps are considered to be effects of three nucleon forces. And then actually, I'd like to note that these results indicate that the significance of isospin-dependent parts of three nucleon forces is going to neutron-rich nuclei, such as helium-8. And another example of three nucleon force effects have been discussed in the equation of state of nuclear matter. As you see that in 2010, the very heaviest neutron star mass have been found. And then the significance of three nucleon forces, especially short and repulsive type of three nucleon forces, are considered to be a key element to understand that heaviest neutron star properties. So in this respect, three nucleon forces are considered to be very important parts to understand that various nuclear properties, as well as nuclear matter. So how to constrain the properties of three nucleon forces? Basically, as it's similar to the two nucleon instructions, three nucleon forces are state dependent. Namely, three nucleon forces are momentum, spin, and isospin dependent. So in order to approach such dynamical aspects of three nucleon forces, Few-Nucleon Scattering system is a good proof. This system has the advantage that one can compare the theory and experiment based directly. Theoretically, it is possible to obtain rigorous numerical calculations based on realistic nuclear potentials in terms of Padif or Padif-Ekbovsky type of calculations. So if we have the precise data of the cross-section and spin observables, and then find some difference between the data and the calculations, we can extract fundamental information of nuclear forces. Here, our interest is Three-Nucleon forces. So where is the hotspot for study of Three-Nucleon forces? In 1998, Henrik Witover and his collaborators proposed that we can see Three-Nucleon force effects in the cross-section minimum region for nucleon-deuterium elastic scattering at around 100 MeV per nucleon. Here is shown a typical picture of angular distribution of the cross-section for deuterium-proton nucleon-deuterium elastic scattering at around 100 MeV per nucleon at rather lower energy region. And then as you see that the contributions based on two nucleon forces have forward peak and backward peak. Forward peak comes from direct term of nuclear-nuclear interactions, and backward peak comes from exchange term of nuclear-nuclear interactions. So that the contributions based on two nucleon forces provide minimum region. Meanwhile, the Three-Nucleon force effects are considered to be constant to the as for the angular distributions because of its shorter range interactions. So that the effects of Three-Nucleon forces are considered to be relatively enhanced in the angular range where the cross-section takes minimum. At rather lower energies, the contributions based on two nucleon forces only are much larger compared to the Three-Nucleon force effects, so that it is hard to approach the Three-Nucleon forces at rather lower energies. Indeed, there are so many beautiful data exist below 30 MeV per nucleon obtained at Tunnel and Kyushu and Cullen by using tandem accelerators. And then the data are beautifully explained by the calculations based on two nucleon forces only. So it is hard to approach the Three-Nucleon force effects at rather lower energy region. So since the prediction or prediction proposal of Henrik Witover and his collaborators, we have extensively performed experiments of nucleon-deuterium elastic scattering at around 100 MeV per nucleon. There are several observables for nucleon-deuterium scattering. The first one is a cross-section. That is a good observable to understand the overall strength of nuclear forces. And then there are several spin observables like as analyzing powers and polarization transfer coefficient and spin correlation coefficients. These observables are obtained by using polarized beams as well as polarized target. Our experiment, here it's shown that the bird's eye of a RIKEN RIBF beam factory, and our experiments are mainly performed by using the RIKEN RIBF beam factory, where we can use polarized deuterium beams. At RIKEN, the polarized deuterium beam is available from 65 to 300 MeV per nucleon, and the polarizations are from 60 to 80% of the theoretical maximum values. The specific feature of RIKEN polarized deuterium beam that we can control the spin axis of polarized deuterium beam is in any direction. So we can obtain a variety of spin observables, including a complete set of deuterium analyzing powers. And also we plan to perform that spin correlation coefficients by using these polarized deuterium beams. At the first stage, we have extensively performed the measurement of the cross-section and all deuterium analyzing powers at around 100 MeV per nucleon by using the magnetic spectrometer SMART. And here is a list of the paper we have published so far. Okay, and then later we extended our experiment to rather higher energies. because as we considered, three-nucleon force effects might be larger when going to higher energies. And then by using this new facility, we have measured all neutron analyzing powers at 3 energies from 200 to 300 MeV/nucleon. And then here is a data table obtained so far for nucleon neutron elastic scattering in the worldwide. And actually, such high precision data set available not only from RIKEN, but also at RCNP, KVY, and IUCF. And here it's shown that a data table of that from 70 to 400 MeV/nucleon, and especially from the cross-section and analyzing powers have been available at variety of energies. However, as you see that polarization transfer coefficient and spin correlation coefficients are rather scarce. In any case, I'd like to note that the discussion of three-nucleon forces via Few-Nucleon Scattering system have, so to say, extensively performed based on a cross-section and all neutron analyzing powers since 1998, and then a data available. A variety of data available. Okay. So I'd like to show our experimental data together with RIBF calculations. Here I compare the data with the calculations based on, so to say, phenomenological nuclear potentials together with Thilson-Melbourne or Urbana-9 nuclear forces. And here is shown that the cross-section data, the angular distribution, at 70 MeV and 135 MeV/nucleon. As you see that a clear discrepancy exists between the data and the calculations, especially in the angular range where the cross-section takes minimum. The blue bands are the calculations based on 2 nucleon forces only. And then these discrepancies are explained by adding the 2 pion exchange of 3 nucleon forces, such as Thilson-Melbourne and Urbana-9 3 nucleon forces. And this feature is also, the similar feature is also observed by taking into account delta aspect citations. So the cross-section, the results of the cross-section show that we can see a 3 nucleon force effects in the angular range where the cross-section takes minimum. And here it's shown that the energy-dependent results of the cross-section and neutron analyzing powers, spin observables, from 70 to 200 MeV/nucleon. The first I'd like to mention for the cross-section, as going to higher energies, 250 MeV/nucleon. We see a serious discrepancy exists between the data and the calculations, even including the 3 nucleon forces at very backward angles. So, and these gaps are actually not resolved so far. And then as for the spin observables, the data are not always explained by taking into account 3 nucleon forces, 2 pion exchange of 3 nucleon forces. So that I'd like to know that so far, the defects of spin-dependent parts of 3 nucleon force models exist. And also serious discrepancy exists at very backward angles as going to higher energies. So this is a summary of the results of the comparison for neutron-proton elastic scattering so far. As for the cross-section at 100 MeV/nucleon, we see a clear signature of 3 nucleon force effects in the cross-section minimum region. So at this energy region, a magnitude of 3 nucleon forces might be okay. However, for the spin observables, the data are always explained by taking into account 2 pion exchange of 3 nucleon forces. So these results indicate the effects of spin-dependent parts of current 3 nucleon force models. And then as going to higher energies, we found serious discrepancy exists at very backward angles. And actually we considered this discrepancy might be cured by taking into account shorter range type of 3 nucleon forces. So in the latter half of my talk, I'd like to mention about progress of experiments. So that's a current. Can you see my talk? Can you hear me? Okay. Can you hear me?
Yes, we can hear you.
Oh, okay. So I'd like to mention about our recent progress of our experiments. So far, we have shown that the first evidence of the three-nucleon force effects in three-nucleon scattering system, and also show that defects of existing three-nucleon force models. But from here, we'd like to start to determine the three-nucleon forces based on Chiral effective field theory by using our experimental data. So we take that cross-section minimum region for nucleon-deuterium scattering at around 100 MeV per nucleon as a golden windows of three-nucleon forces. So along this line, we start the experiments of spin correlation coefficients at around 100 MeV per nucleon. In parallel with this three-nucleon scattering investigation of three-nucleon scattering, we also start the experiments of four-nucleon scattering systems, that is proton-helium-3 elastic scattering, in order to approach isospin-dependent parts of three-nucleon forces. So let me introduce the first part of our recent planning experiment. So recently, that chiral EFT nuclear potentials have achieved to high precision. The fifth order of nuclear potentials reproduce two-nucleon scattering data with very high precision. And then here it's shown that calculated the results based on two-nucleon forces based of chiral EFT and together with our experimental data. And as you see that the similar feature is found in the cross-section minimum region, and also as well as for the spin observables. So we consider that our cross-section minimum region for DP elastic scattering at 100 MeV per nucleon, namely intermediate energy regions, are golden windows to study N4LO three-nucleon forces, the fifth order of three-nucleon forces. And these achievements have pushed us to new projects, that is the determination of chiral EFT fifth order of three-nucleon forces from DP elastic scattering in order to obtain high precision two and three-nucleon forces. And theoretically, the project is in progress by Evgeny Efimov, and they are planning to perform that partial wave analysis of nucleon-deuterium scattering in the framework of chiral EFT. And experimentally, we start the experiments of complete set of spin correlation coefficients for DP elastic scattering at 100 MeV per nucleon to determine the low energy constants of N4LO three-nucleon forces, and also to test two and three-nucleon forces. Here it's shown that diagrams of chiral EFT three-nucleon forces. And so far, mainly three-nucleon forces, so to say, the calculations based on three-nucleon forces available based on by using N2LO three-nucleon forces. But we are planning to approach to N4LO three-nucleon forces. And then we'd like to determine such low energy constants of N4LO. And so far, to my understanding, there are 13 low energy constants of short-range interactions for N4, N3, and N4LO three-nucleon forces. So in order to perform such experiments, currently we are constructing a polarized proton target and also a detector system, and we are planning to perform experiments in a few years at RIKEN RIBF factory. So in parallel with the investigation of three-nucleon forces, three-nucleon scattering systems, we start the study investigation of four-nucleon scattering system. The motivation of the study is as follows. First, this is a four-nucleon, namely a proton-helium-3 elastic scattering. The motivation of the study is as follows. That is a four-nucleon scattering system. So this is the first step from few to many. And then we expect that we can approach to isospin-dependent parts of three-nucleon forces, namely a T=3 half three-nucleon forces. Such three-nucleon forces are considered to be very important in neutron-rich nuclei, as well as neutron star properties. And also we expect that three-nucleon force effects in cross-section minimum region three-nucleon force effects could be seen in the cross-section minimum region as going to higher energies. And recently, the calculations of proton chemistry scattering are available even above four-body breakup threshold energies. So, and here it's shown that the calculated results by Elnaz Deltuba as up to 35 millipernucleon of proton chemistry scattering. And as you see that there is a discrepancy exists between the data and the calculations based on based on two nuclear potentials. So we consider that the proton chemistry scattering, especially in the angular range cross-section minimum region, might be a new rooms for study of three-nucleon force effects in a Few-Nucleon scattering system. So we have already performed the experiments of proton chemistry scattering at 65 millipernucleon and 100 millipernucleon at RSNP in Osaka as well as CIRIC, Tohoku University. And we also constructed a polarized proton chemistry target. So we obtained a cross-section, analyzing powers, and spin correlation coefficient. And here is a list the data obtained so far. And here is a data table available in the worldwide. Blue burns is the data obtained so far in many years ago, and the red circles are the data measured by our group. So as you see that the data are very scarce at rather higher energies, above 65 millipernucleon and 65 millipernucleon. Okay. So I'd like to show some representative results obtained so far. That is a cross-section at 65 MeV, and then a spin correlation coefficient CYY at 100 MeV. And the data are compared with rigorous numerical calculations based on nucleon forces, even including chiral EFT and full LOS two nucleon forces. And also the data are compared with the calculations based on CD bond and nuclear potentials combined with delta-Eisbach citation. The first I'd like to mention about for the cross-section data. As you see, there is a clear discrepancy exists, especially in the angular range, whereas the cross-section minimum region. So that's this feature is quite similar to the results observed in the nucleon-deuterium elastic scattering data. However, we have performed some analysis to show the difference between the nucleon-deuterium scattering and proton chemistry elastic scattering. As for the deuterium-proton elastic scattering at 100 millipernucleon, the discrepancy between the data and the two nucleon forces are removed, explained by taking into account the delta-Eisbach citation as well as three nucleon forces. However, as for the proton chemistry elastic scattering, delta-Eisbach effects, so to say, it gives effective 3 and 4 nucleon forces do not remedy the difference between the data and the two nucleon force potentials. So, in some sense, is that these scattering systems, these two scattering systems, show that some different features. An interesting feature is interesting feature is found in the spin correlation coefficient CYY. As for these observables, a large delta-Eisbach citation effects are seen in this angular range, and then the data are explained by taking into account delta-Eisbach citations. So this feature clearly shows that proton chemistry elastic scattering at intermediate energies are considered to be an excellent tool to explore nuclear interactions which could not be accessible by nucleon-deuterium scattering data, nucleon-deuterium scattering. So I'd like to summarize my talk. Three nucleon forces are taken as key elements to fully understand nuclear properties from few to many and infinite nucleon systems. And nucleon-deuterium scattering, our experiments are deuterium-proton. Deuterium-proton scattering at 100 millipernucleon inspires quantitative discussions of three nucleon forces. And currently, and then in the coming years, we'd like to move on to our project to determination of three-nucleon forces based on chiral EFT nuclear potentials by using our Few-Nucleon scattering data. And by using, especially for the deuterium proton scattering, we'd like to determine the low energy constants up to N4LO three-nucleon forces. And in parallel with this study, we have performed a proton chemistry scattering in order to approach to isospin-dependent parts of three-nucleon forces. And this study performed based on our RIKEN RIBF collaboration and also a proton chemistry collaborations. And Zurich, we also are supported by Zurich theoretical groups. Thank you very much for your attention.
Thank you very much to the speaker for the nice talk. Do we have any questions from the audience? We'll start with Josephine.
Thank you for this very illuminating talk. When you have shown the data of
Deuterium proton?
the data in the early slides, data on DP, they have shown, okay, discrepancy in the backward angles for high energy, but there is at forward angle also some discrepancy for low energy. So to what is it that you?
Thank you very much for your question. You mean this one?
Yes. Yes.
Okay. So this one we consider that comes from Coulomb force, Coulomb interactions.
That was
so that's and then Ernest Tuber and his collaborators performed the calculations taking into account control interactions, and then these gaps are actually explained by taking into account Coulomb interactions.
Okay.
So that so we consider this one is not from three-nucleon forces.
And when you address the discrepancy at a very high energy, at backward angles, what can be, because the role of relativistic effects maybe come into play, is any idea?
That's also a good question. Thank you very much. And as for this relativistic effects, some Olympic collaborations have performed the calculations taking into account rather kinematical effects of relativistic effects, and then in their analysis, in their theoretical analysis, such kinematical effects of relativistic effects do not improve this, the agreements. So that's so far we consider this discrepancy might be come from some nuclear interactions, and then very probably from shorter range three-nucleon forces.
Okay, thank you.
Okay.
Further questions?
I have a comment.
Oh, okay.
For the same picture,
This one?
The same picture, this one, for example, or the previous one. The three-body force that improved the agreement up to, let me say, 100 MeV.
Yes.
Fitted mainly to the triton binding energy, no more than that. So it's incredible, or it's to some extent with only one parameter, it's possible to adjust the cross section up to let me say to 100 MeV. It's clear that above this energy, more flexibility is needed.
Yeah, that's right. That's true.
Joseph?
Yeah, I have a very naive question. Can you put up the slides with the chiral potentials again? The expansion.
Okay.
So,
sorry. Wait a second.
What's going on here?
Now it's 8 o'clock, 9 o'clock, and then the lecture will start.
How long will this last? Okay,
Okay, thank you very much.
awesome. So do I understand correctly that up to now you have 3 fitting constants and you want to go to 13? You know, if you say you want to sort of move everything to the right in terms of the expansion, and then could you comment on, I mean, that seems a big jump, right? So how is this going to be accomplished?
To my understand correctly, how do you, your question is how to determine a 13 low energy constants from our data?
Yes.
Okay, so far we have, there are, as for nucleon scattering, independent observables are 19, and also we perform that energy dependence and also angular distributions. So that's we at least we need some we need 1,000 or 2,000 data to fix these parameters. So that's and also so as for the series side, they perform partial wave analysis, and then we can so to say compare our experimental data and also theoretical calculations, and then fix, and then to obtain and then we fix the low energy constants with to achieve to rather chi-square, and then test the, and we also get that chi-square, and then to obtain a low energy constants with rather less chi-square values. Do you understand me?
Yeah, I understand. It sounds like a very impressive program.
But as you can imagine, that it's very hard task.
Further questions from the audience? Any questions on the internet? No? Yeah, we have a little discussion going on. No?
Question: how many parameters are there for the two-body sector?
We were discussing how many parameters altogether, two-body sector plus three-body sector. We arrive at 36 or something like this. So we were comparing to the parameters of AV18 plus Urbana 9, and we have reached the same order of magnitude. Therefore, it was just an observation that, of course, the AFT is another view, is well found, and it's an expansion. But at the end, if you really want to fix all those experimental data and to predict for body and more, at the end, you cannot do with less than about 40 parameters.
All right, we have independent confirmation of 40 parameters. Good. All right. Well then, if there are no further questions, let us thank our speaker.
Thank you very much.